And we have 5.5 today, polynomial and rational inequalities. So we've been graphing polynomials by their characteristics. We've been graphing rational functions by their characteristics. And now we're going to do the same, but we're going to answer one simple question. Where is the graph above or below the x-axis? So we're going to be getting inequalities that say greater than, less than, greater than or equal to, less than or equal to. So when we start with this polynomial inequality, we're going to graph it the way we've been graphing polynomials, all to answer one question. Where are we greater than 0? Where are we above the x-axis? But let's run through it before we answer that one question. So first off is, given the function, determine the end behavior. And remember, end behavior deals with degree and leading coefficient. What is the total degree of this polynomial?
2.
One more.
3. Oh, because the x times x squared is x cubed.
And that, right? That's
Yep.
x plus 3 to the first and x minus 1 squared. So total degree is 3, which is odd. And then the leading coefficient is that 1 in front. So leading coefficient is 1, which is positive. So we have an odd degree and a positive leading coefficient. What does the end behavior look like?
Down left to the top right.
Good. Down left, top right. Excellent. That's end behavior. And now it says find intercepts, determine the multiplicities. Will we touch or cross? So we're going to take this function and set it equal to 0. So we'll look at x-intercepts first. We let f of x equal 0. And then I take that function x plus 3 times x minus 1 squared, set it equal to 0. It's already factored nice and neat for us. So we get that x equals -3 and x equals 1. So here are my x-intercepts. And now we can answer the multiplicities. What is the multiplicity of -3?
Multiplicity 1.
1, which means it will
Cross at the x-axis.
cross. Good. And then 1 has a multiplicity of
2.
2, which means we will
Touch.
touch. Okay. And the last thing we want is that y-intercept. Where we let x equal 0. We'll have f of 0, and that'll give me 0 plus 3 and 0 minus 1 squared. Here you'll get 3 times -1 squared, which is 3. There's my y-intercept. Okay. Next one's easy money. How many turning points? Well, if the degree is 3, how many turning points do I have?
2.
2, because it's degree minus 1. Okay. Now we have enough information to sketch the graph. So let's go ahead and sketch it, plot the x-intercepts and the y-intercept. So -3 and 1. That's going to go -3 and 1. And then a y-intercept at 3, which is up there. And then we can now graph it by our end behavior. We said we start bottom left and end top right. So this means I'd come up. And at -3, we will cross, go through the y-intercept, come down, hit 1, touch and go. There's our sketch. Okay. And now, all of this to determine where are we above the x-axis. So let me zoom in a bit. So remember that this question asks, where are we above the x-axis? And we only state x intervals. So what interval are we above the x-axis on? Reading it from left to right. Where do we start?
-3.
-3. And where do we stop?
1.
At 1. And then again, from where?
1 to infinity.
1 to infinity. And that's where we are above the x-axis. All that just to answer that little question. Any questions on that process?
So when we determine the degrees in the first step A, or above that, we do not count the degrees of the individual x's inside the parentheses, correct?
You would. That's a good question. You would, depending on the given function. Like, let's say this was x squared plus 3 squared, and then you had x minus 1. What would the total degree of this be?
X to the 4th.
So if you foiled this out, you'd get a high degree of 4, but then you have this one over here.
So it'd be x to the 5th.
So the whole degree would be x to the 5th.
Okay, so as long as the x's inside the parentheses are 1, we do not really count those unless they're at 2 or higher.
Exactly.
Okay.
Yeah. So very good question though. That was good. Okay. And we can also solve these without graphing anything at all, which brings us to the next page. I guess we kind of make a graph. We're going to draw a number line, but here we can solve the polynomial inequality algebraically. So given this inequality, x cubed minus 2x squared minus 3x less than or equal to 0, we're going to do all this work again to answer now, where are we below and on the x-axis? So the first step is to rearrange the inequality. So that step would be important if there were terms on the right side of the inequality. Since all my terms are on the left side, we do not have to rearrange. So I can say step A is done. And then step B, take the given function, set it equal to 0, and solve for x. So we're going to take x cubed minus 2x squared minus 3x. We're going to set it equal to 0 to solve for x. What could I factor out here?
X.
Take an x out. I get x squared minus 2x minus 3 equal to 0. And these are the easy ones to factor. You're going to get x plus a number, x minus a number. And what are the only factors of 3 that could make 2? -2.
-3 and 1.
Good. -3 and 1. This is factored. It's completely factored. And now set each term equal to 0. And you're going to get x equals 0, x equals -1, and x equals 3. Here are my zeros. Here are my x-intercepts. Here are my roots, which means we move on to step C. We create a sign chart, a number line. We plot our zeros, and we'll pick test points on this number line. So C. Here's -infinity. There's positive infinity. And then there's -1, 0, and 3. And then intervals, -infinity to -1, -1 to 0, 0 to 3, and 3 to infinity. Okay, And then test numbers. We're going to have 4 intervals, 4 test numbers. Give me a test number from negative infinity to negative 1.
-2.
Negative 2. Give me a test number from negative 1 to 0.
-1.
-1.
Negative 0.5. Has to be in between the numbers, right? All
Sure.
right. 0 and 3.
2.
2. And 3 to infinity.
4.
400. Perfect.
400. Okay.
It doesn't matter as long as it's in that interval. We could choose 4. We could choose 40, 400. We could choose 4 million as long as it's in that interval. Because all we care about is the sign. We only care about the outcome. So we're going to plug these in to the function. So we're going to have f of -2, f of -0.5, f of 2, and f of 400. Why not? And Desmos for the win here. Let's go.
I mean, just do the math.
Hey, man.
It's not hard.
No,
The
it's
first
not.
one's -2 times -5 times -1. It's negative.
You're right. You're right. But I'm here already. Hey, I'm showing things to make their life easy when plugging numbers in. Let me get this original function. X cubed minus 2x squared minus 3x. Table, bam, come back here. Let's type these numbers in. -2's there already, and then -0.5, and then 2, and then 400. Wow. So like I said, we don't care about the number. We're not graphing anything. We only care about the sign. So here we are, negative, positive, negative, positive. Okay. Back to our sign chart. Okay. So from the interval negative infinity to -1, no matter what number we pick, the outcome's always going to be negative. So this means that we will be below the x-axis. And then from -1 to 0, no matter what number we pick, the output will always be positive, which means we're above, and then negative, positive. And now we use this sign chart to answer the question in the very beginning. I'll say D. On what intervals is this function less than or equal to 0? Basically, where are we below and on the x-axis? So what intervals do we have?
When you say on, are you talking about when the graph touches the x-axis or crosses it?
When it touches, it could even cross it if it had to.
Oh,
right?
okay.
Because we have no idea how this graph looks, but what we plotted on our sign chart, what we plotted on our number line, were x-intercepts, which lie exactly on the x-axis. So that's what I mean by on. It doesn't matter if you cross or touch. So what intervals do we have?
Is that -1?
Good. Negative
Including the
infinity.
-1.
Good. Negative
So the
infinity to
bracket.
-1. We include it because at -1, we are
On it.
on the x-axis. Good.
Hmm.
Union, and where else?
0 to 3 with the brackets.
And that's it.
Yep.
So the brackets are only necessary whenever it's on or crosses the x-axis.
Exactly. When we have also, I guess another easy way to remember it is when you have the symbol less than or equal to, greater than or equal to.
Okay. And what the last question I have is in the previous 5.4 and 5.3, I know we
Yes.
had the rules 1 through 4. Are these rules going to be applying in any of this work here in 5.5?
You may have to graph one using what we did in 5.4. So those rules may come in effect. But then for the next example, I'm going to show you how to graph a rational function, not having to graph anything at all, just doing it algebraically. But if it told you to graph it, then yes, you would go through all those steps that we did in 5.4.
Gotcha.
Okay. But anybody have any questions on that last one? I don't know if it made it any easier that we didn't have to graph it, because with this, when you do it algebraically, you don't have to worry about end behavior. You don't have to worry about turning points. You don't have to worry about multiplicities. You don't have to worry about a y-intercept. but you got to make a sign chart and pick test numbers. All right. Now, let's try it with a rational function. Okay. So we can, just like polynomials, we can solve rational inequalities by graphing and algebraically. All right. So first thing, well, what we're given is 4x plus 5 over x plus 2 greater than or equal to 3. So what we're going to do here is rearrange the inequality and simplify. So this means that when I say rearrange, we need to put everything on one side. So we're going to take that 3, move it to the left. And simplify. So for A, we have 4x plus 5 over x plus 2. I'm going to move the 3 over. You'll have minus 3 greater than, let me space this out, greater than or equal to 0. And the reason I space it out is because we're going to need to combine these two terms, which means 3 has to turn into a fraction. So we put 3 over 1 and multiply by a common denominator of what?
X plus 2.
X plus 2. Multiply this by x plus 2 over x plus 2. Good. And now simplify more. You're going to get 4x plus 5 minus 3 times x plus 2 over the new denominator of x plus 2 greater than or equal to 0. Okay. So the reason I put the numerator together is because we now have a common denominator. So what you're going to do next is distribute that -3. 4x plus 5 minus 3x minus 6 over x plus 2 greater than or equal to 0. And then combine like terms. And we're going to get x minus 1. X minus 1 over x plus 2. There's our new function. Okay. So this is a new function we're going to work with. So next step is find the domain. So B, This is a rational function. So remember that domain comes from the denominator. So we're going to get x plus 2, set it equal to 0, and get x cannot equal -2. There's my domain. Okay. C, find the intercept. So remember, on a rational function, domain comes from your denominator. X-intercepts will come from your numerator. So to make this simple, for your x-intercept, we let this function equal 0, and we just set the numerator equal to 0. And x equals 1. Okay. And then D, we're going to make another sign chart number line. But any questions before moving on? Everybody good with the math that's going on?
Math is the hardest part for me.
Always. Okay. So we make the number line. So D, and we'll make our number line. There's -infinity, there's infinity, and then we have -2 and 1. Give my intervals. -infinity to -2, -2 to 1, 1 to infinity. Test numbers. Three intervals, 3 test numbers. Give me a number from -infinity to -2.
-3.
-3. Give me a number from -2 to 1.
0.
0. And give me a number from 1 to infinity.
15,282.
Sure. Sure. 15,282 just for kicks. All right. And we're going to go ahead and plug these numbers into the new function, right? All of these get plugged into the new function. So I'll have r of -3, r of 0, and r of 15,282. My goodness. Okay, and if I plug in -3, here's for Carl's sake. No Desmos, okay? If I plug in -3, I'll get -4. So I'll get -4 over -1, which means we get a positive output. This means we are above. If I plug in 0, I'll get -1 over 2, which means we get a negative output, which we go down. Then if I plug in 15,282, look what I started. I get 15,281 over 15,284, which is positive. Hey, I like the big numbers though. It just shows you no matter if you pick 2 or 15,000, you're going to get the same result, a positive output, which means we are above. Okay. And now my intervals match. Yep. So we answer the final question. Where is this rational function above and on the x-axis, and or on the x-axis? What's my interval?
-infinity to -2.
-infinity to -2 union. -2 to 1. 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 -2 to
1 infinity.
1 to infinity. All right, not bad. And that's it. That's how we do it. So what's cool about solving these rational inequalities algebraically, or what's cool for you guys, right, is that, again, you don't have to worry about the y-intercept. You don't have to worry about vertical asymptotes, horizontal asymptotes, points of intersection. So all that goes away. But yeah, and I think that's it. That's polynomial and rational inequalities. So we are done with this lecture. So we can use the remainder of this class to answer questions over homework and the test review, since your test is on Wednesday.